Okay, YouTube, in this video we're going to focus on the operation of matrix multiplication. So in the last two videos we've looked at addition and kind of somewhat subtraction, as well as scalar multiplication, which were all very straightforward operations. What I'm going to tell you is that matrix multiplication is not like any multiplication that you've likely seen before. So it's very particular, and we're going to have to kind of pay attention to the rules in this video, but I'll break it down and essentially share with you how you always kind of know how to find the ith row, jth column entry in your product matrix. So let's start with this. We say if A is an m by n matrix, and I want to go ahead and write this here. If we say A is an m by n, and B is an n by p matrix, we have n rows and p columns, then we say the product A times B. If I were to write this product right here, we say is an m by p matrix. So I'm only using C because it's the next letter in the Roman alphabet here. And we would say that this is an m by p. And so what I want to notice here is this, or at least indicate here is this: only defined. Matrix multiplication is only defined if the number of columns in the first matrix, equals the number of rows in the second matrix, equals the number of rows in the second matrix. So if this sounds very confusing, basically what we could write right here is this: the number of columns in the first matrix is this dimension n, and the number of rows in the second matrix is this dimension n here. But we're going to refer to this as the inner dimensions, okay, of these matrices when you line them up side by side. And so in a nutshell here, basically we could say this: we could say inner dimensions must be the same if you want matrix multiplication to work. Now the interesting thing about it is, and maybe I should switch colors here, maybe I could switch over to like an orangey, but basically notice this: on your product matrix, that was the product of your two original matrices, A times B. This matrix here, m by p, you'll notice that these are the outer dimensions here. And so we'll refer to in yellow these two right there as sort of the outer dimensions. But what we can say is this: the resulting matrix will have the outer dimensions basically right here in this product. So we'd say results in a matrix having the outer dimensions of the original factors that we multiplied together, original matrix factors. Okay, so that being said, we just need to know that it's only defined if the inner dimensions match, and we get a product that is having the dimensions of the outer dimensions of the original two. So let's go ahead and take a look at how this is carried out. And I said that it was very particular, so pay close attention here. We say matrix multiplication is row by column multiplication. And if you're confused on this order, just know that when you talk about the order of a matrix, we always talk about the rows first and then the columns, rows by columns, rows by columns. But it is row by column multiplication where the ith row and the jth column of the product AB is obtained by multiplying the entries of the ith row of A by the corresponding entries in the jth column of B, and then adding the results. So here's what I want to notice here. In this particular instance that you see here, we have a 3-row, 2-column matrix being multiplied by a 2-row, 2-column matrix. So the first thing I notice here is that my inner dimensions match, and I notice that I would then get a new matrix that would have to be a 3 by 2 matrix. So what you're seeing right here before we go into the details is this new 3 by 2 matrix. And what this definition of matrix multiplication up here says basically about this row by column multiplication is that if I wanted to, in my new matrix, like this right here, this is in the first row, first column. If I wanted to find my new entry in the first row, first column, what I would do is I would take the first row of this first matrix times the first column of the second matrix, and this is where you see this row by column thing pop up. So we would take -1 here times this -3 and get a number or a value here in this first spot. And then what that says is we're going to multiply the ith row times the jth column, all the entries in the ith row by all the entries in the jth column, and then adding the results. So basically we take this -1 times negative 3. And we're going to add that now to the product of this positive 3 times this negative 4. And basically what we do is we just go across this row as we go down this column, multiplying and adding what we get in each of those. So what I want to notice here is this. When we talk about row by column multiplication, you could think of this row, this first matrix in the product as the row matrix, and this is like our column matrix. And so we're going to take the rows of matrix A, or the first matrix times the columns of the second matrix here, and we're going to multiply and add and multiply and add. So you can see the rest of these here. This is in the first row, second column. So they took the first row entries times the second column entries over here. So we would get negative 1 times 2 coming from this negative 1 times this 2. Now we're going to move over in this row and down in this column. We're going to multiply this 3 times this 1 here. And what we get with both of those products is what we get when we add these together, okay? So this can be done with all of these, and we'll do this by doing I guess we'll do it on our own here, not having it given to us, because when it gets given to you, you kind of have a hard time seeing it. But basically, if we were to take the ith row times the jth column to find the ith row jth column entry in our new product matrix and add all these up, we get this new product right here. So basically, before we do this by hand, one thing I do want to mention is this. I did input these two matrices as matrix A and matrix B in my calculator. You can see this 3 by 2 and this 2 by 2 are those two matrices there. But I just wanted to show you that once you get those put in, you can actually work a matrix product on your calculator as well. And I can say A times B. I get A times B is this matrix here, and I just want you to see that it is the product of those two things and that we can certainly do matrix multiplication on a calculator, but we have to know how to do it by hand. So let's take a look at a product that we'll do by hand. So we're taking the product here, A, B. And so we say A is this 2-row, 3-column matrix times this matrix here that has 3 rows times 2 column, or by 2 columns here. So I noticed that if we're going to do A times B, which is this 2 by 3 times a 3 by 2, that this would be defined because our inner dimensions match. And what we're going to get for an answer is a 2 by 2 matrix. So what I'm going to do is I'm going to rewrite these two matrices side by side. I'll try to use smaller handwriting here. I just fear that it's going to get a lot of clutter here when I try to do this on a bamboo tablet and in Photoshop, but we'll find out here. We would get this product right here, which is the same thing you see over here on the left. So since we can do this, I basically would recommend that you write them side by side, and then the next thing I would recommend is that you write your resultant matrix. And so because I know that I'm going to get a 2 by 2, look, this is a 2 by 2, probably the biggest one you've ever seen me write. I'm going to leave myself some space here, because what I know is I'm going to have to put some things in these spots. We have these 2 rows and 2 columns in this resulting matrix here. So because I know that this first matrix up here I've mentioned is the row matrix and this is the column matrix, here's how we're going to get our products down here. We are essentially going to get our first row, first column entry here, we are going to take our first row entries here times our first column entries in our second matrix. So by clutter, I would say that on my paper I kind of mentally highlight these two things because I want the entry in the first row, first column right here, then I'd better multiply the first row by the first column. So what we get is this. We get 1 times negative 2, which is a negative 2. I want to get those out of the way. 1 times negative 2 is negative 2 right there, plus. Now what we're going to do is we're going to move over in this row and move down 1 in this column, and we're going to multiply now these, the 0 times the 1. So we get 0 times 1, we get 0. Now plus, now we're going to move over 1 more in this first row to the 3 and move down 1 more in this first column to the negative 1. So 3 times negative 1, we get negative 3. So now let's do this. Let's move over here. This would be in the first row, second column. So I can't get rid of these arrows now, but I say first row, I got this one right here, times the second column. In my mind, I'm mentally highlighting these. This is what we're multiplying. But we're going to do 1 times 4 plus 0 times 0 plus 3 times 1, where each time we just move over 1 in the row and move down 1 in the column. So getting those out of the way here, we'd say 1 times this 4 is 4, plus, now 0 times this 0 is 0, plus now move over to the 3 and move down to the 1. 3 times 1 is 3. So now let's go ahead and get our second row and first and second column entries here. Second row is what we're going to pay attention to over here, and the first column would give us our second row, first column entry here. So we're going to go ahead and mentally highlight the second row and first column. but we're going to do this now without those in the way. We say 2 times negative 2 is negative 4. Okay, we'll move over 1 and down 1. We say negative 1 times positive 1 here is a negative 1. Now plus, now move over to the negative 2 and move down to the negative 1. Negative 2 times negative 1 is a positive 2. And then last but not least here we say second row, and I can leave these in this time. I can do it because it's our last multiplication round. Second row, second column, we say 2 times 4 would be 8, plus now negative 1 times 0 would be 0, and then move over and down, we say negative 2 times a positive 1 is a negative 2. So when we add all of these up, we're going to get this new matrix here where negative 2 plus 0 plus negative 3 is negative 5. 4 plus 0 plus 3 is 7. We would say that negative 4 plus a negative 1 is negative 5, and negative 5 plus 7 is a negative 3. Sorry, negative 5 plus 2 is a negative 3. And then 8 plus 2 is a 10. So we got our resulting 2 by 2 matrix. So we have to write these side by side just to help you. But basically we're going to multiply the ith row of the first matrix times the jth row of the second matrix to get the ith row jth entry of our final matrix. So I did indeed also type in A and B here. And what I want to point out here is this. In my matrix menu here, these are C and D respectively. So I have my 2 by 3 and my 3 by 2. I'm going to pull this out. I'm going to say C times D. Get those out here. And I say, look at what we get here. We get this negative 5, 7, negative 3, and 6. So I want to check my last multiplication here. And I did actually make a mistake looking at this. This negative 2, I apologize for this. This negative 2 times the positive 1 would have been a negative 2. And maybe I even said negative 2, but 8 plus a negative 2, this would be a 6 here. But just know that you can check these on your calculator, and for good reason, because see, I'm human and I missed a negative on this one. So my last question is matrix multiplication commutative? Now when we talk about the commutative property of multiplication, when we talk about real numbers like A and B, we know that A times B is B times A. My question is, with matrices, is A times B, we'll put a question mark here, is it equal to B times A? So one thing to keep in mind is this: if I were to do B times A here, I would now be taking a 3 by 2 times some 2 by 3 thing, and I certainly can do this in certain instances if the inner dimensions still match. But I want you to notice here, what I would get is some new matrix that would be a 3 by 3 matrix. So already what I can tell you is, because I got a 2 by 2 over here, there's no way that B times A, being a 3 by 3, would be the same thing as A times B. And so I want to show you here, if we actually do this on our calculator, not the long way here by hand, which we still should be able to do, we'd say D times now matrix C. We would get a 3 by 3 where we would take now the rows of B times the columns of A, and we would get this new matrix here. So we would say that matrix multiplication is not always commutative. It is only in certain circumstances commutative. Cheers.